Welcome to lecture number 40 of this statistical thermodynamic course for engineers. So if you look at it here, we already saw that for a diatomic molecule, what are the different contributions? What are the different contributions that you are going to have for a diatomic molecule? So we already saw that for a diatomic molecule, okay, the contributions part, that what are the classical contributions of the translational, rotational, vibrational modes. Okay, so we are going to continue in this line, and we are going to write that by invoking equipartition principle, okay, we can determine the internal energy and the heat capacity as it is summarized in the table just above. Okay, so the translational mode, if you look at it, translational mode, okay, that is characterized by three, altogether three, okay, pure quadratic momentum terms. Pure quadratic momentum terms. Okay, quadratic momentum terms. Okay, one for each translational degree of freedom. Similarly, the rotational mode, okay, the rotational mode actually has 2 degrees of freedom, which basically corresponds to two pure quadratic okay, momentum terms. Okay. Now the vibrational mode, on the other hand, okay, this has got only 1 degree of freedom, but it has got 2 independent quadratic terms, one based on momentum, and the other is based on position. Okay. The additional quadratic term arises from its potential energy, okay, which was missing in the translational and the rotational modes. So the summary of the classical energy for a diatomic molecule displays, so if we write it properly, the classical energy for a diatomic molecule, okay, is composed of 7 pure quadratic terms. The implication is an internal energy and heat capacity per mole is therefore. So this implies that internal energy U will have something like 3.5 RT, and this CV will have something like 3.5 R per mole, as distributed among the 3 classical energy modes. These are distributed among 3 classical energy modes. All right, classical energy modes. So for monoatomic gas, okay, however, we have only 3. We have only 3 quadratic translational contributions. Okay, and therefore the U will be like 1.5 RT, and CV will be 1.5 R, which is 3/2 R. Okay, so the classical predictions for internal energy and specific heat agree very well with the quantum predictions for monoatomic gases. However, the agreement is quite poor for diatomic gases because except at temperatures approaching 1000 and 2000 Kelvin. This behavior can be understood if you take into consideration the characteristics mode temperatures. Okay, you recall that translational and rotational modes have characteristic temperatures much less than 300 Kelvin, whereas the characteristic temperature of the vibrational mode is much greater than 300 Kelvin. Therefore, the translational and the rotational modes are fully excited, thus matching their classical contributions at room temperature. Vibrational mode approaches full excitation only at much higher temperatures. On this basis, we would expect that diatomic energy, internal energy, and heat capacity per mole to be like 2.5 RT and 2.5 R respectively near room temperature. Okay, so the influence of temperature on the specific heat for a diatomic molecule can be shown like this. Let us draw this figure so that it is easily understandable. Okay, so this is the temperature. This is CV by R. So that what we write is basically, and let us put 3 demarcations now. And this is already known. Let's extend it a little bit. Okay, so let's mark it at 3 by 2. So this is translation. Starts here and then starts to pick up. And it goes like this. Okay, so this is pure translation. This is translation. Okay, and here the temperature is greater than equal to theta R, which is approximately 10 Kelvin. Okay, so this is translation plus rotation. Okay, and then it starts to pick up once again. Somewhere there. Okay, so this is valid when temperature is less than equal to theta vibration, which is roughly of the order of 1000 Kelvin. Okay, so this part is now translation plus rotation plus vibration, something like that. Okay, so what did we learn? If you look at this particular table, we would see that the classical, that's what we said, that the classical predictions are good for monoatomic gases. Okay, that's the first point. Second point is that they are poor for diatomic gases. Except when the temperatures approaching is about 1000 to 2000 Kelvin. Okay, 2000 Kelvin. Okay, so this behavior, as we already said, that translational plus rotational modes are fully active at T less than equal to 300 Kelvin. Okay, vibrational mode, they are fully active or fully excited, whatever you call it. Okay, but however, the vibrational modes are active at T exceeding about 1000 Kelvin. Okay, so that is a full excitation level. So and this is what is shown in this particular figure. Initially it's all translational. Then as soon as about we reach 10 Kelvin, the rotation starts to kick in. So there is a jump. And then it starts to increase once again when we have this marker of about 1000 Kelvin. Okay, so that is the basis. Okay, so the temperature, influence on temperature on the specific heat follows this kind of a behavior. The plateaus that we see signals full excitation of an energy mode. So here where it plateaus, that means all the translational and the rotational modes are fully activated. Here it means all the translational modes are activated. This growth period shows that the rotational modes are getting activated. Okay, not all of them are activated. This is the same transition which shows that vibrational modes have started to get activated. And this is the full activation or the full excitation of all the vibrational modes as well. Okay, so this fascinating behavior actually reflects that using quantum mechanics and statistical thermodynamics, when applied to gaseous systems, we will see how the specific heat of a gas actually undergoes these very nice transitions. Okay, so we have provided so far a methodology for determining, let us see what we did by statistical thermodynamics. We have provided a methodology for determining the most probable macro state, considering an isolated system. The most probable macro state, in fact, showed that internal energy and entropy in the dilute limit, okay, expressions, okay, and we have successful analytical expressions for all intensive thermodynamic properties of an ideal gas. Now, these properties are expressed in terms of a partition function, right? So all properties, we know, all properties are expressed in terms of the partition function. In terms of the partition function, right? In terms of the partition function. So that is what we saw, right? And which is Z, which requires two informations, EJ and GJ. Okay. So obtaining such data, how do you get this? These two information comes from quantum mechanics plus spectroscopy. Right. This also we saw. Now we have access to the spectroscopic information. We can now finally calculate the properties of an ideal gas. So our motto is to calculate the properties of an ideal gas. This is our motto, and this is what we are going to do in this particular lecture and the next one probably. Okay. However, we should do it. We can start with a monoatomic gas, which requires only the translational and the electronic modes. There is no rotation and no vibration. Okay, then we can go to diatomic gas, which requires information on the rotational and the vibrational energy modes. And then, of course, one can consider polyatomic gas, okay, which is basically multiple atoms. So monoatomic gas has got the advantage. Monoatomic gases, this has got two modes. One is translational, and the other one is electronic. Okay, so no rotation or vibration, not possible, right? Because it's a single atom. Similarly, of course, you have for the other types, for the diatomic gases, of course, you have a lot of other things. So monoatomic gas, useful, there are quite a few useful examples like helium, argon, okay, elemental radicals like atomic hydrogen, atomic nitrogen, and atomic oxygen. For such gases, rotation and vibrations are irrelevant. So we consider only translational and the electronic energy modes, right? So based on the extremely low characteristic temperature, the translational mode will produce thermodynamic properties that are closely associated with classical mechanics. Contributions from the electronic mode will come at a much higher temperature, right? So this is the situation. So the classical mode is very well represented by the translational mode, or the translational mode very well follows the classical mode, okay, so to say. Okay, so for a single gaseous atom, so first let us look at the translational mode. Okay, so here energy translation is h squared divided by h m e third, n1 squared plus n2 squared plus n3 squared. Okay, three spatial quantum numbers. N1, N2, N3. Okay, that can take up any value. This can have any values from unity to infinity. Okay. So the contribution to the thermodynamic properties from any independent energy mode can be ascertained by determining its contribution to the partition function. So partition functions can be evaluated most directly by basically summing all these up over the states rather than the levels. So therefore, Z translational is given as, first we sum N1 equal to 1 to infinity, N2 equal to 1 to infinity, N3 equal to 1 to infinity. Got it? Okay, and then we write exponential for minus sign h squared h n e third 80. Then you have n1 squared plus n2 squared plus n3 squared. Okay, so the partition function, the generalized expression for the partition function for the translational mode is therefore given as summing over n1 equal to 1, or n rather, n equal to 1 to infinity, exponential theta t n squared by t, where theta translational is written as h squared divided by 8 m a v. V is the volume, so therefore I just cut it across. Okay, so we have introduced what we call the translational temperature. Translational temperature. So so summing over all possible values of unity to infinity, we are indeed accounting for each quantum state as identified by its unique set of quantum numbers, because there's a cube involved, okay, over here. So we recall that theta t was basically 10 to the power of minus 16 Kelvin. Okay, so any realistic assembly temperature can be converted to an equivalent integration now, okay, because incredibly minute separation between consecutive energy translation and energy levels, we have a continuous distribution of translational energies, continuous distribution like in classical mechanics. So the discretization is rather poor. So incredibly minute separation between two consecutive translational levels. Okay, so it leads to an almost continuous distribution of translational energy. Energies. Okay, so Z translational is equal to 0 to infinity. Okay, exponential minus theta t n squared by t dn. Okay, cube. This integration, if you perform, it will lead to half I t by theta t cube. If we substitute this, the Z translational energy therefore becomes 2 pi mkt by h squared whole to the power of 3 by 2 into p. So this is the translational partition function. Okay, can be also done over energy levels if you do the summation of energy levels using the density of states. or evaluating the phase integral. But this is what it will get. There are varieties of ways to calculate it. This is the most important classical analog. Okay. So quantum mechanics is largely unnecessary for this, because the equipartition principle is perfectly suitable for calculating the translational contributions to the thermodynamic properties. This is almost the classical equivalent, right? So the characteristic temperature of the translational mode is so small that the total number of quantum states is essentially equivalent to that of the translational mode. So therefore, using our criteria for dilute limit, okay, Z by N is almost equal to the Z translational by N, which is equal to 2 pi mkt by h square, okay, 3 by 2 E over N should be much greater than 1. Okay, for any ideal gas, say we take an ideal gas at say 298 Kelvin, which is the room temperature, and 1 bar. This is STP basically. This gives Z translational by N to be a number of equivalent to 10 to the power of 5. Okay, so it means that the total number of quantum states is almost the same as that of the translational. Okay, so employing the translational partition function, now we may evaluate the contributions of the translational mode to the thermodynamic properties of an ideal gas. So URT, the translational component, is T ln Z translational divided by dt at constant volume. This becomes equal to 3 by 2. Similarly, for specific heat, it is Cv by R translational, it is equal to d by dt t square d ln Z translational by dt. Is also equal to 3 by 2. Therefore, the translational contribution to the internal energy is 1.5 RT, and to the specific heat capacity is 1.5 R, which is as you expect from the equipartition principle. Okay, so for specific enthalpy also, so if we look at specific enthalpy, that is H by RT translational, this will be equal to 5 by 2. And Cp by R, the specific heat at constant pressure, that will be 5 by 2. The specific enthalpy and specific, so this is specific enthalpy, and this is specific heat constant pressure. Okay. So at this point, the pressure can be determined also by combining aspects of classical and thermodynamic properties. Okay, so that so pressure is given as minus P is equal to dA by dV E comma N. So where your A is basically the Helmholtz free energy. This you all know. Helmholtz free energy. Which is given as minus nkt ln Z by N plus 1. We did all these things earlier also. Therefore, P will be equal to nkt ln Z by dV constant temperature. So PV would be equal to nkt, okay, which of course is the equation of state for an ideal gas. Equation of state for an ideal gas. Okay, so the obvious implication is that pressure arises solely from translational mode. Okay, so as it is expected, because it's the momentum exchange at all walls at the independent gaseous particles. Okay, so on the basis of this, we can then write all the other partition function for each internal energy mode must depend solely on temperature. Okay, so then similarly we can write it for entropy, we can write it for the other types of properties as well. So now you can see from this particular work, the most important statement was the how the pressure is actually varied. The translational modes are so dense and so gigantic in numbers, they supersede all the other modes that are available. So in the next lecture, we are going to see that how we can write entropy. For example, we'll do a sample problem, okay, which will be on Helmholtz free energy, and then we will look at the contribution from the electronic energy modes, which is a little bit more involved than the other modes, right? So that will enable us to calculate the properties of a monoatomic gas, because as we say that the monoatomic gas essentially depends on the translational and the electronic mode. It does not depend on the vibration of the rotation because they don't exist anyways. Okay, so we end the lecture here. We will convene with a few more, a little bit more detailed understanding of the electronic mode.